In this video, we're going to focus in on the alkene hydrocarbons, so the hydrocarbon that has an E in its name. And these are ones that are going to have carbon-carbon double bonds, and that double bond adds some complexity to our structure, so we've got a little bit more to talk about. So alkenes are hydrocarbons with at least one carbon-carbon double bond. And here's our general formula. We've got CnH2n. So notice it's not 2n plus 2, now it's just 2n. The reason we lose two hydrogens, so we go from 2n plus 2 down to just 2n, is to go from all single bonds. So here we have an alkane with 2 carbons. It would have 6 hydrogens, the 2n plus 2. If I want to make a carbon-carbon double bond, to put that double bond in there, I have to have 2 fewer hydrogens. So now, to give this carbon 4 bonds, it only needs 2 hydrogens. Same with this one. So now we're at a value of 2n. So if I do the same process I did back with alkanes, 6 carbon atoms, we're going to do 2 times 6, so we've got 12 hydrogens. If we know we have 8 hydrogens, that has to be equal to 2n, so n must be 4. You want to go ahead and pause the video and try the last 2, and come back and check yourself. So with 9 carbons, 9 times 2, 2 times 9, 9 times 2, same thing, is 18 hydrogens. And then 32 has to be equal to 2n, so that means there must be 16 carbon atoms. For drawing alkenes, it's a very similar process as it was to alkanes. You're first going to attach everything with single bonds, all your carbon atoms. Then you're going to add a double bond somewhere. And if you're given just a formula, which is all you are at this point, you can put it anywhere. Once we get to naming these molecules, the name will give you the exact location. But for now, just stick it between 2 carbon atoms. It doesn't matter which 2. So if you're drawing these structures and checking them with my answers, they could be different. Again, you're going to fill in your missing bonds with hydrogens to make sure that your carbon has 4 bonds total. So if we go in and try this first one, we've got 6 carbons. I'm just going to pick any bond and make it a double bond. I've got 12 hydrogens, so if I look at this carbon on the left, it currently has 2 bonds, so I'm going to give it 2 hydrogens. The second carbon over already has 3 bonds, so it only needs 1 hydrogen. And it does not matter if you draw that on the top or bottom, same thing. Next carbon over has 2 bonds, so it needs 2 hydrogens. Same for the next 2 carbons. And then the one on the other end needs 3. So if you count up those hydrogens, you should have 12. Next example, we've got 4 carbons. This time I'm going to put the double bond in the middle just because I can, doesn't matter. The carbon on this end needs 3 hydrogens. Both of them with the double bond this time have 3 bonds already, so they need 2. Again, top bottom for those hydrogens doesn't matter. Then the carbon on the right has 1 bond, so it needs 3 hydrogens. So there are the 8 hydrogens. Again, go ahead and pause, see if you can draw an alkene with 5 carbons. All right, if it's got 5 carbons, we know it should have 10 hydrogens. So let's see if we can get that to work. There's 5 carbons. I'm going to stick the double bond down on this end this time. So the far left, we need 3 hydrogens. Next 2 carbons need 2 hydrogens. And remember, everything we're trying to get to 4 bonds. The next carbon already has 3 bonds, so it needs 1 hydrogen. And then the one on the end currently has 2 bonds, so it needs 2 hydrogens. So there's your C5H10. To look at 3 dimensions for the alkene, it's not shown in the picture here, but this is a double bond. Okay. The drawing tool that was used doesn't actually draw in the 2 lines, but that is the double bond. If you look at a carbon that's on the double bond, it has 3 bonding groups. Remember, the double bond counts as 1 bonding group, and then the 2 hydrogens will count as 2 more. So 3 bonding groups. There are no lone pairs, So that's going to be trigonal planar. If we look at any of the other carbons that are single bonds, the rest of the molecule in this case, those are all tetrahedral because they have 4 bonds. But if we look at the carbons that are part of the double bond itself, they both have 3 bonding groups, so they're going to be trigonal planar. One other thing that is different about double bonds versus single bonds is that they don't rotate. So single bonds are constantly rotating, the molecule is always moving around, but a double bond can't rotate, it's locked into position. So that means depending on what type of groups you have, you could have different orientations. So in this example, here's our carbon-carbon double bond. It's right underneath this line that's drawn, okay? So if I look at the carbon on the left of the double bond, it has a hydrogen attached and a CH3 group attached, okay? So doing this process, you have to look at both carbons of the double bond and make sure there's 2 different groups attached to both of them. So the one on the left has a hydrogen and a CH3. If I look on the carbon on the right, it has a hydrogen and a CH3. So both carbons have 2 different groups attached to them. So now you want to compare and see if the groups are on the same side or the opposite sides. So usually I look at the carbon groups because when we get to another way of drawing this later, you won't actually see the hydrogens to compare them. So the carbon groups are on opposite sides of the double bond, so that means these are trans. If I look at the example on the right, this carbon on the left has a carbon and a hydrogen. The one on the right also has a carbon and a hydrogen, so it's good to have either cis or trans. This time the carbon groups are on the same side, which means that it is cis. Okay. If you ever look at your double bond, so if I look at this one again, for example, if it had 2 hydrogens or 2 carbon groups on it, we wouldn't be able to have cis or trans. And you have to have 2 different groups coming off of each of the carbons of the double bond. Let's look at a few examples. Again, for me, it helps to kind of draw a line through the double bond so you can kind of see what is above and below that line. In this case, we've got a CH3 group, so a carbon group coming off of the carbon on the left, and a hydrogen coming off of that carbon on the left. So that's 2 different groups, so we're good there. If I look at the carbon on the right, I have a carbon group. It doesn't matter how big it is, it's a carbon group, and a hydrogen. So again, I've got 2 different groups. Now if I want to compare the 2, the carbon groups are on the same side, so that means this molecule is cis. If we look at the second example, again, I'm going to draw a line through the double bond. If I look at the carbon on the left, I have a carbon group and a hydrogen group. If I look at the carbon on the right, I have a hydrogen group and a carbon group. So again, I'm good, 2 groups on each carbon. Now if I compare the 2 carbon groups, they are on opposite sides of the double bond, so that is considered trans. All right, then we've got one more example. I can draw my line through the double bond. If I look at the carbon on the left, I have a hydrogen and a carbon group, so I'm good there. If I look at the one on the right though, I've got 2 carbon groups. So because these 2 groups are both carbon groups, this molecule is considered neither. So it's not cis or trans. Because if I compare these 2 groups, they're on opposite sides and it would be trans. If I compare these 2 groups, they're on the same side and it would be cis. So we call that neither. We'll look some more at cis and trans when we name our alkenes in a later video. So some physical properties of alkenes, they are typically gases or liquids at room temperature, just like the alkanes were. Also, just like alkenes with 2 to 4 carbons are going to be gases. The ones that have 5 or more are going to be liquids. Now, if we want to compare alkenes to alkanes, the alkene will have a slightly lower boiling point than the alkane. So we've already said we don't have hydrogen bonding, we don't have dipole forces. The only difference is size. So if I can compare the alkene to the alkane, we had the CnH2n for alkene, CnH2n plus 2 for the alkane. So that means the alkane is a little bit bigger, making the boiling point a little bit higher. And it is a very slight difference. But we will always rank the alkene boiling point as lower than the alkane. As far as geometry goes, here is a trans double bond. Here is a cis double bond. So the trans, you have that zigzag pattern much like we did for alkanes. You can stack these pretty easily. So if I put a couple more in here, they stack relatively well. That means you have good interaction between the molecules, which makes the boiling point a little bit higher. If I look at the cis version, you kind of have this kink in the molecule that makes them more difficult to stack. Okay, so that means the boiling point is going to be a little bit lower. So we've already said that alkene boiling point is lower than alkane. And then if we want to split the alkenes out into cis and trans, cis is going to be lower than trans. So here's a couple examples. I want you to rank the boiling point from, I just want you to pick out the one that's going to have the highest boiling point. So the one on the left, we have an alkene. And if we check for cis and trans, we have groups that are on the same side. So the carbon groups are on the same side. So that's going to be cis. The one in the middle, everything is single bonds. So that's an alkane. And then the one on the right are double bond. The groups are on opposite sides. So that's going to be trans alkene. So if we go back to our ranking, alkanes always have a higher boiling point than alkenes, so that means it will be the highest. And then the cis alkene will be the lowest.